Okay. So this is the myosin. Okay? So hold it in the center. So this is the myosin. These two rulers will be actin. Remember, myosin has the heads. So the heads are going to reach up and grab onto the actin and slide them forward. And then they're going to let go and grab again and slide it forward. And they're going to let go and grab again and slide it forward. Yeah. So then the edges, where the two rulers are, is a relaxed muscle. And then when it's contracted, they're closer together. So the entire muscle takes up less distance.
So it's these that are doing the
Right. It's the myosin heads that are pulling it forward. And we'll cover how that does that on Tuesday when we do the physiology. Okay? But these clusters of bundles of actin and myosin are the myofibrils. Now, for the myosin to grab onto the actin, it has to have that binding site exposed. And the requirement for exposing the binding site between myosin and actin is calcium ions. So, if we want our muscle to be relaxed, we have to get rid of the calcium. If we want our muscle to contract, we have to dump calcium into the cytoplasm of the cell. So that brings us to our next structure, which is this blue membranous structure. And you're already familiar with this. It's endoplasmic reticulum, but it's not ribosomal endoplasmic reticulum. It's closer to smooth. And in the muscle cell, of course, we use the muscle name. It's called sarcoplasmic reticulum. And it stores calcium ions. So when the muscle cell is relaxed, there's very little calcium in the cytoplasm. It's all stored in the sarcoplasmic reticulum. And the nerve signal, the electrical current, triggered in the muscle cell by the release of neurotransmitters. That electrical current opens voltage-gated channels for calcium, just like we saw in the synaptic bouton. And calcium will come rushing out of the SR, the sarcoplasmic reticulum. So in our anatomical content, which is what we're just covering today, I'm going to kind of diagram this on the board. So we have the plasma membrane, or sarcolemma, of our muscle cell, and it's going to form a neuromuscular junction with our lower motor neuron. This is the lower motor neuron. And the synaptic bouton releases neurotransmitters, which we'll talk about this in more detail on Tuesday, acetylcholine. It binds to ligand-gated channels. Don't worry about understanding all this. It's what we're going to talk about on Tuesday. I'm just trying to get us, if there's enough ions coming into the cell, that will open voltage-gated channels and the rest of the sarcoplasmic membrane. Remember, that's called sarcolemma. The muscle membrane, sarcolemma. Okay. Now, if we need to open voltage-gated channels deep down in the muscle cell, in the sarcoplasmic reticulum, having the current way up here in the surface isn't going to do it. So we need to carry that electrical current deep into the cell. And we do so by taking the sarcolemma, and it's like taking, I don't know how many of you have made bread dough or yeast bread. When it rises, you can take your finger and push it in, and it makes this little indentation. So it's like somebody stuck their finger in the muscle cell and created these evaginations of plasma membrane. And so these are evaginations that fold deep into the muscle cell and go around our bundles of actin and myosin and then come back out again to the surface. These have voltage-gated channels in them as well. So if this is a voltage-gated channel for sodium and potassium, we have to allow extracellular fluid deep into the cell. Or if we open up a sodium channel, there'll be no sodium to cross it. So So these structures, known as transverse tubules, carry that current deep into the cell as well as extracellular fluid. So I'll redraw this on Tuesday when we talk about how they actually function instead of just naming them. Question, Angelique?
I'm sorry, what did you say it carries in there?
The extracellular fluid, so this would have a whole bunch of sodium ions in it as well as out here. So we can continue to send that action potential.
So those are hollow.
Well, they're hollow, yes, and they're containing interstitial fluid, extracellular fluid, the same as we see up here.
What kind of ions? I'm sorry.
These would be sodium. Okay. Now, they're wrapped around the myofibril, or the myofibril. And so we have I'm going to draw the sarcoplasmic reticulum first because it's covering. So the sarcoplasmic reticulum is going to be wrapped around our bundle of actin and myosin. So this is a sac, remember, that is storing calcium ions. So this structure is the same as this blue structure here, and it's known as the sarcoplasmic, instead of endoplasmic, sarco for muscle, sarcoplasmic reticulum. And it stores calcium ions. Now there's a special area of the sarcoplasmic reticulum right here. If I were to draw that in cross-section, here would be the transverse tubule or T-tubule containing extracellular fluid, hollow with this fluid. And on either side of it would be sarcoplasmic reticulum that's dilated as it comes close. So this area right here would be this area right here. So this would be the sarcoplasmic reticulum. Now, this area that's very close to the T-tubule has a property similar to the axon hillock. What was the special property of the axon hillock? It would have low threshold, so it was very easy for it to stimulate the voltage-gated channels because it had such a low threshold. Same thing with these two areas. They have a very low threshold, so as the current travels down the transverse tubule, it's easy for this area to have their voltage-gated calcium channels opened by the current in the muscle membrane. And so that special region of the sarcoplasmic reticulum is known as the terminal cisternae. Now these three structures together are known as a triad. So this is a cross-section of this area right here. Okay. So if we look on the diagram, this whole thing is the sarcoplasmic reticulum. The yellow line is the transverse tubule. On each side would be the terminal cisternae. Okay. So we'll stop there.